This is actually a progress being made by the initiative titled Smart Construction Program, sponsored by Korean government. And I'd like to talk about this topic, smart technology for scaffolding safety, based on three conference papers that I recently co-authored. One of them is from ICCEPM 2022. It was last June in Las Vegas. And this ISAR paper is from Bogota, Colombia. It was, I think, last month. And this was also from the ISAR 2022. So based on these three conference papers, I'd like to talk about the smart safety insurance technology for temporary structures. First of all, I'd like to talk about how we can check the safety of joints of temporary structures. Well, Professor Park gave us a very wonderful statistics information regarding the notorious record of this industry, construction. In fact, scaffolding is a major part of that, not the favorable statistics. For example, according to Korea Occupational Safety and Health Agency, the temporary structure related accident is accounting for more than 40%. So you can imagine how significant handling this issue is when it comes to construction safety. And in the right figure, you can see this joint area. And in many cases, when this joint is not properly installed or assembled, these temporary structures, scaffolding, tend to collapse. Now, people are looking and watching to find out if there is any safety issues related to the scaffolding joint. But what we are suggesting is this drone-based monitoring with the help of deep learning and computer vision. So this figure basically shows you the process of getting the safety information for the joint. First of all, we have to get the data from UAV. To do that, we first identify the area of joint. Then we go deeper to find out the component of each joint. Then the combination of this component can help us figure out whether or not any particular joint is safe. So in this figure, for example, you can see that the left figure is safe because this tail of P is properly installed. But in the right figure, the tail is missing. Then you can easily think that this joint could easily become a cause for the collapse of that particular scaffold. So the methodology goes like this. As the first step, we identify the joint. And this was done by one of those state-of-the-art object detector called YOLO 5. Then after we identify this joint area, then we extract component information such as ledger end and standard and pinhole and tail. Pinhole is identified because we want to check the quality of this image. For example, we are using UAV, and UAV is flying near that target object of scaffolding. What that means is UAV can take lots of pictures of that scaffold. So every second, 30 frames are in general taken. Then we don't have to use every image. We can use only those good quality images. And to check that whether or not that image in our hand is good, we are checking the existence of this pinhole in that image. So if pinhole is shown, that means this image is angled image, which is not good. So using this kinds of analogy, we can check how good the quality of each image is. Yeah, this is what I'm talking about in terms of poor quality images. Pinhole is shown or something is occluded. So we are looking for this good quality image, which is not angled images. So once we identify that good quality images, then we can successfully detect this tail and ledger end and standard. Based on the combination of this, we can determine this is safe and this is unsafe. With the testing, after getting lots of data and, of course, training data and validation data and testing data, they are all separated from each other. And the result was actually very good. This figure shows you, this video is showing you the first step of this proposed method, the joint detection part. And this figure is showing you the component detection part. We see some problematic results when it comes to detecting pinhole part, but when it comes to understanding the overall safety of each particular joint, we got very good F1 score. In terms of safe joint identification, it went up to even 98%, but we need to get more data to have more robust and more reliable methodology. So conclusion, basically, this UAV-based monitoring of scaffolding is working up to now, and we got very high F1 score, so it is promising. However, UAV is one of those smart mobility that we can rely on. Unfortunately, in many parts of Seoul, we're not able to use UAV, drone, because of the security issue. I'm working for Yonsei University, which is quite close to a place called Blue House. Blue House means the residence of the president of South Korea. Up until last year, we were banned from flying drone here because it was too close to that Blue House. But from this year, the president moved to another office. So if we ask for it, then yeah, we have the approval from some authority which allow us to fly drone, but still we have to get the approval first. So it's not easy to fly drone on construction site. Not just that, flying drone has also some downside too, for various reasons, which I do not want to I do not want to spend time on explaining. So I try to find a way to use other smart mobility, such as robotic dog, for getting the point cloud of scaffold. I'm showing you another version of statistics. Again, it's painful to share this statistics. Construction industry account for more than half of the casualties of industry of Korea. In fact, this bad record of construction industry in terms of safety is applicable to many parts of the world. And if we do a bit of more analysis, as Professor Park said, fall accident is very, very important major cause of this construction fatality. And in that, we also see scaffolding is also one of those biggest portion, accounting for about 20%. So again, scaffolding is critical element when it comes to safety issue, but time and cost are required to manually supervise the activity of the scaffolding installation and dismantling. So we are trying to use smart mobility, such as this, for leg robot for automatic inspection. So we are proposing a new framework to fully automate the laser scanning process. Yeah, this is fully automated. So this is system architecture, which is composed of 3 parts. First of all, data acquisition and mapping. We use sensors such as LiDAR and IMU. In this case, we are using mobile laser system. So this LiDAR data combined with this IMU data are fed into our SLAM algorithm. Then obviously we can have registered point cloud data. Then in the second step, this point cloud data are converted into 2D image based on this bird eye view projection. We can deal with the 3D point cloud data as they are, but computationally it's expensive. So we are compressing the amount of data into a smaller scale by using this bird eye view projection. Then we can use any kinds of state-of-the-art detector to identify scaffold location. Then the next step is intelligent moving around of this robotic dog. The robotic dog now understands where it is supposed to go, and it plans its movement. And as you can see, over time, our SLAM data, our SLAM result will be strengthened more and more. So the robot is equipped with more and more knowledge over time. So we can see, even later, the robot can change its path planning, its operation path. This is our robot. This is not the robot produced by the Boston-based company, which was recently purchased by Korean conglomerate, the car-making company. And this robot is, in my opinion, was able to walk around on the site, and it didn't produce any particular problem so far, but this particular version is not that tall. So as a matter of fact, this robot cannot climb up the stair of a regular architectural building, but still it can manage to walk around the construction site when the site is a bit processed, a bit prepared for the robot walking. And as you can see, we have mobile LiDAR here, an IMU sensor, and this robot has its own onboard computer. This is basically hardware architecture. So the first part, if I give you a bit detailed explanation, the first part is, again, data acquisition mapping. And you can see this algorithm called LeoSAM. This is one of those state-of-the-art SLAM algorithms. And these algorithms are based on 4 extra information, such as odometry and GPS and IMU and closure, but we are here not using GPS. And you can see that this is our test bed on Yonsei University campus, and this is registered point cloud. The second step is real-time scaffold detection and registration. This SLAM algorithm provides now the map of the site to the robot. Then bird eye view projection is executed. And based on this image resulting from this bird eye view projection, now we can detect scaffold. Of course, each unit, each read box of the unit is trained in advance. Then based on this training, our robot is becoming more and more knowledgeable and intelligent. Then based on that intelligence, the robot can now detect the location of these target objects. In other words, scaffolding. We can talk about some strengths of this proposed methodology. And bottom line is this is real-time process. The robot doesn't have to have prior knowledge of the site. It can just start to move, and over time, its map result is more strengthened. So the robot can keep doing its job of understanding the environment and scanning the target object. In this case, in this project, which is, of course, scaffolding. So left figure shows you the SLAM-based bird eye view projection result. And right figure is showing you obstacle avoidance picture. We are using LiDAR data to implement this obstacle avoidance algorithm. And the last part, scan planning and navigation. And you can see some node here, which is, for example, in the beginning, it pre-scan. So basically, the robot is actually checking out what's going on roughly. Then it selects the target scaffold. Basically, robot identify the goal as to where it's supposed to go. Then it strategizes a plan in terms of what is the candidate scanning point. Scanning point means the location that robot is supposed to go. Then out of this candidate, robot can choose actual scanning point, then move to the scanning point. And once it arrived there, and it just change its angle and its face. So basically it rotates to face the target object, and it starts to scan. If the point, the number of points of the point cloud data is going over a certain threshold value, then move to the next scaffolding point or even next scaffold. Otherwise, it goes back to other scanning point location. So this is closed loop process based on this SLAM result, which is getting better and better over time. We even calculated the scanning distance. The scanning distance is needed because robot better not be too close to the target object. The LiDAR has this field of view. When the robot is too close to the target object, then probably the top portion of the target object wouldn't be able to be scanned well. So it distances itself, the robot distances itself from the target object to a degree. Then our robot can do this kind of motion. Trust me, robot is not suffering from anything. Robot is just moving its part to make sure that it provides the maximum view to our LiDAR. So we did some experiment, and in terms of detecting the scanning point and scanning the scaffolding structures, we got F1 score of 0.796. And you can see how robot is doing. Our researcher is sitting here, and this was one of those days where lots of mosquitoes are there. So he had this specially equipped special hat. But trust me, he's not controlling this robot. Robot is operating on its own, and it's making its movement to measure and scan this target object, and we succeeded in obtaining these temporary structure point cloud. So conclusion, basically, we succeeded in developing this autonomous robot operation algorithm, and hopefully this can be more and more robust enough to be applied to more complex construction sites. Finally, we used multi-class 3D segmentation to understand better of the safety of the installed scaffolding. Again, some statistics that pretty tragic. So we have to do something about this. And we actually extracted 3 well-known KOSHA guidelines, which regulate the attachment status of a work platform, and attachment status of stairs, and attachment status of guardrail. I'd like to show you how our technology is able to provide answer for these 3 KOSHA regulations. This methodology shows you the basic process. First of all, we get the point cloud data, then multi-class segmentation, then this rule-based algorithm check the safety of that particular target object. We secured 4 construction sites, and from this site, we get the data, and we, of course, separated training and testing data. And this is what is referred to as the segmentation algorithm, which is actually RenderLanet, one of those state-of-the-art semantic segmentation artificial intelligence. We got the weight from other domain, so we retrain this portion of this RenderLanet. So we can say we use transfer learning. Those of you who are not familiar with this scaffolding structure, I'm very nice, I'm very kind enough to explain this. This is stairs, and this is work platform on which the construction workers walk and do their jobs. And this is guardrail. This is upright. This is bracing. So our job is to identify these elements accurately, and based on that, we will make a judge. We will judge whether or not if this scaffolding structure is safe. This is some rule-based algorithm that we developed. Basically, we modified concave hull algorithm to extract these kinds of scaffolding structures from point cloud data. Then we started to check with regard to these 3 regulations. The main concept of this checking flow is potential field. Based on the geometrical properties, based on those geometrical properties of the target object, we can predict which area of that 3D point cloud is the potential field for each element. So we check if the potential field has the corresponding element. That's the main part. That's the main mechanism of this algorithm. So this is for guardrail potential field. The same principle is applied here. Then we did some experiment for multi-class segmentations. One problem is this bracing. Bracing has very low F1 score because we didn't have much data of this bracing point cloud. But this had no significant effect on the overall accuracy of that status checking of scaffolding structure. And I think it's premature to say this now, but later we actually strengthened the data for this bracing class 2. So based on that elements that I illustrated, now you see how this scaffolding structure is composed of. And we identified 13% potential field, and we purposely identify these areas. For example, here we can see that this work platform is missing. So work platform is missing in this case, and that was accurately predicted. But below that, we see stair. So in terms of this regulation, this is okay. However, here we see 2 missing guardrail elements. That was accurately identified from this experiment. So conclusion, yep, this laser system LiDAR was used, and it has, according to this experiment, big potential for accurately understanding the safety status of scaffolding structures on site. So to conclude today's presentation, the progress made by this research program titled Smart Safety Assurance for Temporary Structures were introduced in 3 aspects. First of all, UAV-based joint detection, then 4-legged robot operation, then finally, LiDAR-based multi-class segmentation. And UAV and 4-legged robot were used to provide smart mobility to those sensors, whether it is image sensor or laser sensor. And SLAM, simultaneous localization and mapping, and semantic segmentation, and rule-based algorithms were also integral parts of the proposed methodology, and they are currently tested on real construction site. Right now, at this particular point in time, my lab members, my researchers are on the construction site provided by Korea Express Corporation, and they are testing these technologies that I'm just talking about here to improve their performance and improve their robustness. So this is acknowledgement. Korea Research Foundation, National Research Foundation Korea, and the Korea Agency for Infrastructure Technology Advancement under the Ministry of Land, Infrastructure and Transportation, and managed by Korea Express Corporations. All of these organizations, I give them many thanks, acknowledgement. So that concludes my presentation. Any question or comment would be greatly appreciated.